Let me start with, I guess, a bit of a correction well, we're talking about path independence in the context of work integrals. And I started out saying uh, you, you have a conservative vector field if and only if curl of f equals 0. That's not exactly true for you rigorous mathematicians. It is certainly true that if f is conservative, then the curl of it is 0. The converse is not always true in every case. You can find exceptions to it, meaning that the curl of f equals 0 does not necessarily in all cases mean that f is conservative. But in my course and in most problems in vector fields, it's pretty safe to say that if the curl is 0, then the vector field is conservative. The real way to determine if it's conservative is if you can find the potential function. But in my course, this was also a method. If the curl was 0, then you could assume it's conservative. If you want to be rigorous about it, this does not necessarily imply a conservative. So I was doing examples and talking about the easy method. Let me do more examples. This one. This was a problem I put on some of my exams, and actually it was on the exam I took back in 1970 something. Gives you the vector field and asks, does that vector field have a corresponding potential function? If so, what is it? And then evaluate the work integral along the path shown. It has two parts, from here to here on a straight line, and then from here around there on this helix. Well, actually, if you look at that vector field, oops. If you look at this thing I showed in my last video, that if your vector function, it's p, q, and r, and if p is only a function of x, q is only a function of y, r is only a function of z, then its curl is 0. And that's close enough to say it's conservative, but it's certain that the curl is 0. And if you look at this vector function, that is true. P is only a function of x, y is only a function of, actually, it's any of them. P is only a function of z. So you can look at it and say, yeah, it's probably conservative, but we need to find the phi. So we use my easy method. Integrate p with respect to x, you get x squared. Q with respect to y, you get y. R with respect to z, you get z. No repeats, you add them up. There's your phi. Let's check it. Its gradient is going to be 2x, 1, 1, which is f. So this is our phi. So now we can evaluate this guy. And now here's a trick. And every semester, or every time I give this problem, some student does it the hard way. All that matters is where you start and where you end. You don't need to do each leg independently. Remember, it's independent of path. So it's going to be this phi evaluated at this endpoint, 104 pi, minus this phi evaluated at the start point, 120. Make substitutions, you get that, and it simplifies to this angle. That's the moral of that. Don't evaluate each leg. It only depends on where you start and where you stop. Another example of the easy way, if you're not getting it yet, this is only P and Q. It's only two-dimensional. There's our P, there's our Q. If you put it in vector format, there it is. Let's see, integrate P with respect to X. I'll get X squared Y squared minus 3X. Integrate Q with respect to Y, I'll get X squared Y squared plus 4Y. That x squared y squared is a repeat of that. The whole phi is going to be x squared y squared minus 3x plus 4. Check it. And yes, indeed, that equals your vector. I won't go through this partial integration the hard way, I guess. Look at it yourself. Partial of p with respect to y is 4xy, and the partial of q with respect to x is also 4xy. That's the curl of 0, which indicates conservative. Find the phi. At least in my course, one way to think about path independence is if the problem looks ridiculously hard, if you try to do it the normal way. And here's an example I put on one of my exams. Evaluate this work integral, where the path consists of these two straight line segments, pieces, curves. If you tried to do it the normal way, it would get way tedious and seemingly out of hand. So just hope it's path independence. Let's see, here's our P. With respect to X, you get XYZ plus XZ squared. Right? This guy with respect to Y, you would get XYZ Y squared. This guy with respect to Z, you get XYZ Y squared Z XZ squared. You add them all together without the repeats. Add XYZ and add XYZ are repeats of this. This XZ squared is a repeat of that. This Y squared Z is a repeat of that. So this is all that's left is your phi. Take its gradient. Lo and behold, it is the F. Yes, it is conservative. We found the potential function. And again, only go from start to end. Starts at 111, ends at 222. Check. Here's our phi, 222 minus phi at 111. And here's the arithmetic, and there's the answer. Sometimes you're not given the start and end points explicitly. You might get r as a function of t, and it says, where's t go from? Well, you just plug in. It starts where t equals 0, or 1, 1. Ends where t equals 1, 2, 3. That's path independence. Other subject video.